Hello, welcome back to Senior Study Buddies. Today we're talking about chemistry and specifically the periodic table. The periodic table, though it looks daunting, is very important and actually very easy. It's very important because in order to really be successful in chemistry, you have to understand what's on this table and why it's on there. It looks scary, it looks disorganized, but there really is a method to this madness. First, we'll talk about the history briefly. The periodic table was basically put together to show us trends and groups of elements. As new elements were discovered, we had to have a way to catalog them by their differences, their similarities, and by their trends. And the first person to really do this in a modern way was Dmitri Mendeleev. He's generally associated with the first periodic table, and though he didn't know of all the elements we know of today, the skeleton of his periodic table is basically the same as the one we have now. We've added some elements, we've changed it around a little bit, but it was generally the same. Like I said, the purpose of the periodic table is to show us trends and to basically organize the elements for us in a way that's easy to read and easy to understand. So the first thing to know about the periodic table is that the elements are arranged across in order of atomic number. The atomic number is the number of protons in an atom of an element. For example, hydrogen, number 1, is the first element, has 1 proton. We skip all the way over to number 2, which is helium. It has 2 protons. 3, lithium, has 3 protons, so on and so forth. The arrangement, you might ask, if it's only from atomic number, why isn't it a line, why isn't it a basic square or rectangle? That's because along with atomic number, it's also arranged in order to show us distinct groups and distinct trends that are easily observed by this shape, but could not be observed if it was in a square or rectangle. And you'll see that later. So some features of the periodic table. The periodic table consists of periods and groups. Periods are rows across, groups are rows up and down. So period 1 consists only of hydrogen and helium, 1 and 2. Period 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, so on and so forth. And then we have groups, which are the rows up and down. The first group, group 1, starts with hydrogen, lithium, sodium, potassium, all the way down. Group 2 is beryllium, magnesium, calcium, all the way down, on and on and on and on. We generally say there's 8 groups, which is these two. And then 3, 4, 5, 6, 7, and this says 0, but we can think of it as 8. And then later, as you move into the transition metals, we add groups, but those are the main 8. Okay, so now we'll go ahead and talk about the different distinctions or groups that are very important to know on the periodic table. First of all, we have group 1, which, as I said, starts with hydrogen, goes all the way down, and those are what are known as the alkali metals. This is a very important group because they all react the same. They're very explosive in water. They're actually very reactive metals because they form a 1+ charge when they become ions. And the reason for that is because this group right here, their valence electrons consist of only 1 electron. So on their outer shell, there's only 1 electron. It's very easy for them to lose that lone electron. When that happens, they lose 1 negative charge and they become a 1 positive ion. So we'll see later that they match up very well with the halogens, which become a 1 negative ion. The next group, the alkaline earth metals, very similar. However, because they have 2 valence electrons, they form a 2 positive charge. This is a little bit different. They're still very reactive, some of the most reactive metals. However, instead of a 1 positive charge, they form a 2 positive charge. They're a little bit less reactive because it's harder to lose 2 electrons than it is to lose 1. And you'll see that later. They match up with group 6, which has a 2 negative charge. Alright, next I'm going to move all the way over to group 7, which is the halogens. It starts with fluorine, chlorine, bromine, iodine, astatine. This group is very significant because, like I said, they have 7 valence electrons, meaning they, in order to gain 8, need to gain 1. It's much easier to gain an electron than it is to lose 7. So they gain their 1 electron to have a full octet, and that gives them a 1 negative charge, meaning they match very nicely. with the alkali metals that have a 1 positive charge. Next, we have the metalloids. This is an odd group. Starts with boron, then we go down into the side, silicon, the one under it. We move over, and then down again, and we basically stare all the way down, and it's a diagonal. Those are the metalloids because they're not, they don't always show characteristics of metals. However, they are metallic in certain aspects of their characteristics. Next, we have the nonmetals, which are anything to this side of the metalloids. Nonmetals, they pretty much explain themselves. They're not metals. Then after that, we have the metals, which are anything under and to this side of the metalloids. So as you can see, most of the periodic table is metals. Anything in this block from here to here is what's known as the transition metals. They can lose electrons, gain electrons, and many times have different charges. So you can't always know what charge a transition metal is going to have. Many of them do create the same charge whenever they make an ion. However, some of them change. Next, we have these two odd groups down here, the lanthanides, and under them is the actinides. And they look like they stick out, but really they fit into this table. However, it's more convenient to show them down rather than have a whole long list at the bottom. So as you can see here, there are two elements, La, and under it's Ac. That's lanthanum and actinium. And basically, all of this first row fits in after La, but before HF. And then under it, the second row, the actinides fit in after actinium and before RF. So you can kind of see that they would fit in. However, having this would make it very inconvenient to have the periodic table on a single sheet of paper. That's not the only reason, but I think that's the main reason that they include them lower. So even though they look separated, they're really in here because their trends put them in here. And last but not least, we have the noble gases, which is group 8 or group 0, depending on what your periodic table says. And that is helium all the way down through xenon, and some people probably have radon. These are called the noble gases because they have no valence electrons, or some people say they have 8 valence electrons. Either way, their outer shell is full. So they do not gain any electrons, they do not lose any electrons. They're already happy, as you could say. So because of that, they do not react easily. Actually, they hardly ever react at all. That's why they're called the noble gases, because generally people think of nobility as stuck up and don't like to associate with other people. So you have the noble gases. Next, and probably most importantly for most people, I'm going to talk about the trends on the periodic table. The groups that we talked about, though they might be hard to remember sometimes, they're generally easy to understand. However, the trends can sometimes be tricky because there are a couple things we have to keep in mind. While I'm talking about the trends, there are two things that you really need to understand. The first is electron shielding, and I'm going to go ahead and say electron shielding comes into play as you go down a group. The second is effective nuclear charge, or just the nuclear charge, and that comes into play as we go across the group, or rather across the period. Electron shielding, it's basically what it sounds like. As you go down the periodic table, new rows of electrons are added. The outer shell of electrons for potassium is much farther away from the nucleus than the outer shell for lithium or hydrogen. That's because as electrons are added, the levels they're added to can only hold so many. You can kind of think of it as like planets orbiting around the sun. If all the planets orbited at the same level, they would crash into each other. However, because they are staggered in distance away from the sun, they don't crash into each other. And that same goes for electrons. Because electrons are so small, some of them can be in the same level. So for example, for hydrogen and helium, which are in period 1, their outer shell can hold 2 electrons. Hydrogen's only holds 1 generally, and helium's is full with 2. We go down to the next group, and that can hold 8 electrons. So as we move across, electrons are gained until the 8th one is gained and the outer shell is full, and then a new outer shell is gained for sodium. This again can hold 8, and we keep going. So as we go down, not only are more electrons added, but they are added farther away from the nucleus and in different levels. Electron shielding basically says that as electrons get farther away from the nucleus, the bond between the negative electron and the positive proton becomes weaker and weaker. This is because obviously they're farther apart, but also because the electrons inside of the outer electrons shield the charge. They kind of absorb some of the charge. So these outer electrons are much less attracted to the nucleus than the inner ones. And that kind of makes sense, and that explains a lot of the trends that we're going to talk about. Next is effective nuclear charge, which also has to do with charge, but in a different way. This applies as we go across a period. So as we go across a period, like I said, the atomic number goes up by 1 for every element. That means 1 proton is being added, and generally means 1 electron is being added. So we'll look at period 2. Lithium, in its outer shell, has 1 electron, and that corresponds with 1 proton in the nucleus. So you can think a 1-to-1 ratio, the charge will be 1, we can say. It's actually neutral because they're equal. However, the bond between them is as strong as a 1-to-1 ratio. Then we move on, and it gains an electron and it gains a proton. So now it's 2 and 2. So as you can see, the bond between them is stronger because say you have 1 magnet and 1 magnet and you pull them apart, it'll be kind of easy. If you take 2 magnets and 2 magnets on the other side and put them together and pull them apart, it'll be a little bit harder. If you get all the way down here, say to chlorine, and you have 7 magnets in one hand, which would be the 7 electrons on the outside, and 7 magnets in the other hand, which will be the 7 protons in the nucleus, it's going to be very hard to pull them apart. So basically what that means is as you add electrons and protons going across a period, the bond between the electrons on the outside and the protons in the middle becomes stronger. So those two things, electron shielding and nuclear charge, or effective nuclear charge, are basically what determines trends across the periodic table and down the periodic table. Remember, electron shielding applies as you go down, and effective nuclear charge applies as you go across. So first we'll talk about atomic radius, and we'll talk about everything in terms of going down and going across. Atomic radius is basically the radius of an atom. Because electrons orbit in variable ways and we can't really measure them exactly, the way this is found is 2 of the same atoms are bonded and the distance between their nucleuses is found, their nuclei. And then this distance is divided by 2 because you think 2 electrons bond and that's the outside. So basically it's the size of the atom. And I know you learn about ionic radius is the same thing, the size of the atom from the nucleus to the outside of the electron cloud. So as you go down, and this is pretty obvious probably to most of you, as levels are added, the atomic radius rises, it increases. That's pretty obvious. As more levels are added, they become farther away from the nucleus and the atom becomes larger. So now we look going across. As we go across, protons are added and electrons are added. You may think that because electrons are added, this makes the atom larger because it's getting larger and larger. But we have to remember that the electrons are being added to the same level. So what that means is that the atom isn't getting any larger. Electrons are just being added to the same level, and protons are being added to the same nucleus. But because the nuclear charge increases as we go across, that means that as more electrons are added to the same level, and that doesn't increase the size of the atom at all, because the charge between the electrons on the outside and the protons in the middle are stronger, it actually pulls those electrons in tighter and makes the atom a little bit smaller. That sounds confusing that you're adding electrons and it's getting smaller, but really it makes sense because you have to think about it in terms of the nuclear charge. The size isn't changing because the electrons are added to the same level. However, the charge is increasing and it's being pulled in tighter and tighter, like those magnets we talked about. So atomic radius, ionic radius, the same thing, it's size. And as we said, as they go down, it increases because the electrons get farther away, new levels are added, and because the electron shielding decreases the charge on these outer electrons. They kind of stray away from the nucleus and make the atom become larger. As we go across, atomic radius decreases because though electrons are added, they're added to the same level, and as the nuclear charge increases, this pulls the electrons closer into the nucleus and makes the radius of the atom smaller. Next is ionization energy. This is the energy it takes to remove an electron from a gaseous atom of an element. And again, we'll think of it in terms of electron shielding and nuclear charge. So, as we go down, and more electrons are added, the ionization energy is going to decrease, meaning that it takes less energy to remove an electron. And again, this probably makes sense because as you add electrons into new farther and farther levels as you go down, these electrons are less attracted to the nucleus because they're farther away, and also because the electrons inside of them are kind of shielding that charge. So as you add them farther and farther away, the charge is less and less, and it's easier to take them off. Another example of that is the magnets again. As you hold magnets close together, they're very hard to pull apart, but as they get farther and farther, they become less and less attracted to each other, and it's the same principle. Next, we're going to talk about across a period, and the same principle applies, the increased nuclear charge. So across a period, because of the increased nuclear charge, ionization energy increases. Same way as before, as new electrons are added, the effective nuclear charge becomes greater because it's more negatives on the outside and more positives on the inside, and they're pulled together tighter. This means that the bond between them inside the atom are greater, and it's harder to pull them away. So you see that for sodium, this will have a lower ionization energy than all the elements to the right of it, and that is because its nuclear charge is not as great as the ones over here. So ionization energy, the energy needed to remove an electron from a gaseous atom, it decreases as you go down, and it increases as you go across. Next is electron affinity. This is the ability for an atom to gain an electron. And it basically follows the same principles as before: electron shielding as you go down and nuclear charge as you go across. So electron affinity, as you go down, new electrons are added to the outer level. This means that the charge that the nucleus has on the rest of the electrons is less. So it has less charge to pull in another electron. However, when we're up here and there's not a lot of levels on the outside, the charge, you can think of it as almost magnetism, is great because there's not a lot of electrons shielding that charge. They're not absorbing it, so it can suck in extra electrons if they're floating around. As we go across, the same principle: increased nuclear charge, more electrons are added, which means more protons are also added as we go across, and that results in a higher nuclear charge, which means that it is more able to attract an ion, rather more able to attract an electron. So we'll see the same principles. Electron affinity, as you go down, it decreases, and as you go across, it increases. Last is electronegativity. Electronegativity is a number 1 through 4, and basically it's the measure of an attraction of an atom for the electrons in a chemical bond, and that's kind of a convoluted way to explain it, but it's sort of like electron affinity. It's basically the reactivity of the element, and it follows the same trends. As we go down, it decreases because levels are added and the charge of the nucleus is shielded by the electrons around it. As more are added, it's shielded more and more. As we go across, electronegativity increases because the nuclear charge increases as more protons are added, and this means it's more reactive. So we look across, fluorine, which is the first halogen, actually is the most electronegative element of any elements on the periodic table. It has electronegativity of 4. This 4 gradually decreases as you go down, like I said, and as you go across this way, it gradually decreases. So the highest is fluorine, and the lowest is somewhere down here. I couldn't tell you exactly which one. Like I said before, the noble gases are happy because they have full outer shells. That means they're basically exempt from all these things, especially electronegativity. They don't want to gain electrons. They don't want to lose electrons. They're not going to become ions. And they actually don't have an electronegativity. I don't think it's even 0 because they just don't even have it. They're not reactive at all. They're not going to gain. They're not going to react with anything. So they don't have an electronegativity. And lastly, boiling point. Boiling point is a little bit different. It doesn't have as much to do with electron shielding and nuclear charge. What it does have to do with is the type of bonding that goes on between atoms, and also van der Waals forces. So we'll see with boiling point, it's a little bit complicated, but as you go across, it increases, okay, and then it decreases. And then as you go down, it increases. The reason it increases as you go across is because the metallic bonding between these metals gets stronger and stronger as you go to the last couple metals. Then when you hit the metalloids, it's basically some of the strongest metallic bonds. But then we hit carbon and silicon, and they actually form what's called a network covalent bond. This is the strongest bond possible. It's the strongest bond there is. And that's why you have things like diamond, glass, which is silicone. They have some of the highest melting points of any substances or chemicals. Then as we go into the nonmetals, the boiling point greatly decreases to some of the lowest. That's why your nonmetals are often gases and sometimes liquids, whereas your metals are usually solids. So like I said, it bunny hops, it goes up. It generally goes up as you go across until you hit about group 3 or 4, and then drastically falls. And it's kind of unpredictable, but that's just a general rule you can follow. And then like I said, as you go down, the boiling point increases. And this is not because of electron shielding, rather this is because of van der Waals forces. If you've learned about van der Waals forces, it is the random attraction of atoms because of electron configuration around the nucleus. So it's important to know that van der Waals forces increases as the mass of the atom increases. That's because there's more electrons, there's more weight to be thrown around, and the chance of a random attraction happening is greater. So we'll look at the halogens, for instance. They have very low boiling points. However, as you go down, the mass of each halogen increases. And what this does is it increases the boiling point because the van der Waals forces between them, which keep them together, is greater. So boiling point bunny hops across, generally rises all the way until the end of the metals and then falls drastically. And it increases as you go down because van der Waals forces increases the attraction, and it increases with mass. So as they get bigger, the boiling point becomes higher. I know one thing a lot of people do is try to memorize all of these trends, and I never did that because I felt like it was much easier to understand the main 2 topics, which were electron shielding and nuclear charge, and also understand what each trend was: atomic radius, ionization energy, electron affinity, and electronegativity. If you want to memorize whether they increase or decrease across a period or down a group, you can do that. However, I felt it was easier, and I felt I've retained it more because rather than trying to memorize it, I tried more to understand the concept of electron shielding and what that means for charges and attractions in an atom, and also nuclear charge and how that changes as you go across and what that means for the atom. If you understand those 2 things and you know what each category is, for example, atomic radius is the size of the atom, ionization energy is the amount of energy it takes to remove an electron, those things, if you understand electron shielding and nuclear charge and you understand the 4 trends and what they actually mean, you don't have to memorize whether it increases or decreases across or down, because basically you can just apply those principles and figure it out every time you look. And then eventually, once you understand it well enough, you won't have to look anymore. You'll just know. So if you're just going to memorize it for the test, that's one thing, that's good. However, I greatly urge you to really try to understand these concepts because they're going to come up no matter what as you go through chemistry. That are the trends of the periodic table. That is the periodic table. I would like to highlight a couple things. Most importantly, that we've learned today are electron shielding and effective nuclear charge. They help you with this. They're going to help you later, and they basically explain why a lot of reactions do or don't happen, and why a lot of trends across the periodic table are or are not there. So just remember, electron shielding is the adding of electrons to outer levels. They get farther away from the nucleus. The charge is shielded by the inner electrons, and they're less attracted to the nucleus. Effective nuclear charge is the attraction between the nucleus and the valence electrons. And as more electrons are added to the same level, they stay the same distance. However, the charge from the nucleus kind of pulls them in closer and makes that bond stronger because there's more electrons and there's more protons. You can almost think of them as magnets, and that's, I think, the best way to understand them. So that is the periodic table. I hope it helped you understand. I hope it helped you with what you're learning in class. If you haven't listened to this, she does a great job of explaining it, but sometimes it's helpful just to hear from another person. If you see me around school, ask me. As you can tell, I love to talk about chemistry, so I'll answer any questions you have. And besides that, thank you for tuning in, and have fun studying.